In part B of the problem, we'd like to calculate the electric field at point P, which is arbitrarily located on the x-axis. Now, there's more than one way to do this calculation. You can either use the results from previous problems, or you can calculate this from scratch. So I'm going to calculate it from scratch. In order to do that, we are going to start with an area element dA. So that's going to be a two-dimensional element dA, and dA will act like a point charge with charge dq on it. So here's my area element dA with charge dq. Now, because this is a disk and it's all symmetric, it makes sense to use polar coordinates to express dA. So we are going to express dA in terms of the polar coordinates r and theta. Let's remember the area element in polar coordinates. In polar coordinates, we have r and theta. R is the length coordinate pointing radially outward from the origin, like so. And theta is the angle measured counterclockwise from the positive axis. So this is the theta coordinate. And here's my area element dA. It looks like a rectangle with slightly a curved rectangle. Now let's try to identify each side of this rectangle, and then we'll come up with an expression for its area. Now, how can we express this side of the rectangle? Well, if you think about it, this is the direction of the radial coordinate r. So an infinitesimal displacement in this direction is called dr. So that side of the rectangle is basically di. Now, how about this side here? This is the arc length, and the angle corresponding to this arc length is d theta right here. Remember the arc length formula. The arc length is equal to the angle corresponding to the arc length times the radius times the distance from the origin. While in this case the radius here, or that distance, is defined as r. That's my coordinate r. So this whole distance here is r. That means the this curved side of the rectangle is equal to r d theta. So then that makes the area of a rectangle is the product of its two sides. So then the area element in polar coordinates is equal to r d theta dr, or r dr d theta. Again, the flat side is dr, and the curved side is the arc length, which is equal to d theta times r. Now I have an expression for the area element in terms of the polar coordinates. Now we can go ahead and express dq in terms of the given variables and the coordinate variables that we came up with. Remember, by definition, the surface charge density sigma, which is a given variable, is equal to total charge divided by total area, right? But it's also equal to, it's also defined as the unit charge divided by the element the area element. So dq divided by dA. Let's substitute what we just found for dA in terms of the polar coordinates and rearrange the equation to isolate dq. So we get dq equals sigma times r dr d theta. Next, we are going to set up our integral and calculate the electric field E at point P. Now, this is a three-dimensional problem, and in principle, the electric field vector should have three components. It should have a x component, y component, and the z component. But because there's a lot of symmetry in this problem, it turns out all the y components and the z components will cancel and only the x components will survive. So to calculate the electric field, the total electric field at point P, we only need to integrate over the x components of the electric field vector. Now let me show why the y and z components cancel out. Now this is the electric field vector dE due to a point charge dq. Imagine another unit charge dq on the negative y-axis at the same distance as the first dq that we have on the picture. Now this unit charge dq will create an electric field that looks like this. The electric field created by the second particle that I picked on the picture cancels out the y component of the first one, right? So the y components cancel because the two electric field vectors are symmetric, and the x components will add up because both point upward. So only the x components will survive. Now, if you think about it, for any arbitrary point charge dq that you select on the disk, there's going to be another one on the opposite side at the same distance that will cancel out either the y or the z components, or both of the y and z components, and only the x components will survive. So the magnitude of the net electric field at point P is equal to the integral of the x component of dE, integral of dEx. Now let's identify dEx. Let's come up with an expression for that. I'm going to call this angle alpha right here. Here's my vector dE. The x component is this segment on the x-axis, so this is dEx. What is dEx equal to if this angle is alpha? It's equal to dE times cosine alpha. Like so. So now let's find an expression for cosine alpha in terms of the given variables, or the variables that we come up with to solve this problem, the integration variables. So if that's alpha, this angle here is also alpha. Let's focus on the triangle formed by point P, the origin, and the point charge dq. In other words, this triangle right here. I can use this to come up with an expression for cosine alpha. The adjacent side for alpha is the segment from point P to the origin, and that's basically x. That's the coordinate of point P, x coordinate of point P. And the hypotenuse of this triangle is the distance between point P and dq, right? What is the hypotenuse equal to? I can find it from the Pythagorean theorem using the distance from the origin to dq, and that's basically the coordinate r, right? So that's defined as r. Now again, this is x. That's the coordinate of point P on the x-axis. This distance here is r, and the hypotenuse is going to be equal to the square root of x squared plus r squared. And here's cosine alpha. Cosine alpha equals adjacent divided by hypotenuse, which is x divided by square root of x squared plus r squared. Again, in this problem, x is a constant. That's where point P is located. That doesn't change. Lowercase r is one of our integration variables. That's the coordinate of elementary charge particle dq. Now let's go ahead and set up our integral. I have substituted the formula for dE. Basically, this is the formula for electric field strength due to a point charge, which is charge divided by 4 pi epsilon 0 times the distance squared. The charge is dq, and the distance from dq to the point of interest P is the length of that dashed line, green dashed segment, which is the square of that distance is x squared plus r squared. Now we need to multiply this by cosine alpha. which is equal to x divided by the square root of x squared plus r squared. In the next line, I'm going to substitute dq with the expression that we found above. Also, I'm going to combine the two like terms in the denominator, x squared plus r squared. So basically, we have the same term to the first power and then to the square root of the same term. So we'll just combine those, adding the powers. Now that we have our integral expressed in terms of the actual integration variables, we can also go ahead and add the lower and upper bounds for those variables. The variable r runs from capital R1 to capital R2, and theta runs from 0 to 2 pi. Next, I'm going to pull all the constants outside of the integral and also separate out the dr integral and the d theta integral so that we can see everything clearly. Now let's go ahead and take this integral. The integral of d theta is simply theta, so that's easy. The second integral, r dr divided by x squared plus r squared to the power 3 over 2. We can take this integral using a u substitution, and here's how we can do that. If we set u equals x squared plus r squared, du becomes equal to 2 times r times dr. Now in the next line, I took care of the d theta integral, and I also rewrote the dr integral in terms of our variable u. Note that the lower and upper bounds have also changed. So the du integral is running from x squared plus r1 squared to x squared plus r2 squared. So let's take this integral. The result of this integral is negative u to the power minus 1 over 2. Now let's evaluate our integrals. And here's the result of our integral. So next, I'm just going to simplify this expression. The term in the middle, 2 pi minus 0, that's simply 2 pi. And for the square bracket term, I'm going to switch the order of the two terms inside the parentheses to get rid of the overall negative sign. Note that the 2 pi in the numerator is going to cancel or simplify the 4 pi in the denominator, so we'll just have a factor of 2 left in the denominator. And here's our final result after those simplifications. This is the magnitude of the electric field at point P, and the direction is in the positive x direction, upward or away from the disk. If point P was somewhere on the negative x-axis, the electric field would again have the same magnitude as this, x being absolute value, of course, and the direction of the electric field will point down in the negative x direction, in other words, away from the disk again. Why? Because, again, the disk has positive charge distribution.